Controls drift over time, validate continuously. The slow betrayal, while your security posture lies to you. There is a particular kind of organizational disaster that never announces itself. It does not arrive with an alarm or a failed deployment. It accumulates quietly, in the space between the policy document that describes how a system should be configured and the actual configuration running in production right now. The gap between those two things is what practitioners call controls drift, and understanding it, not just as a concept but as a persistent organizational condition, is one of the more important disciplines in security work. Here is the failure mode in its most recognizable form. An organization builds a security baseline. They harden their servers against the CIS benchmark. They configure their firewall with a minimal explicit allow list. They deploy file integrity monitoring on their critical configuration directories. They complete an audit, everything checks out, and the auditors go home satisfied. And then nothing. The organization moves on. Engineers ship new features. Developers request temporary exceptions. A patch is applied that quietly modifies a configuration value. A team member troubleshooting an outage at 2 in the morning opens a firewall rule to isolate the problem and then goes home to sleep, intending to close it in the morning. The morning comes. The ticket is not created. The rule stays open. 2 years pass. When the next audit arrives, or when a penetration test surfaces a critical vulnerability that should have been blocked, the question everyone asks is, when did this happen? The honest answer is almost always, gradually, slowly, in the space between decisions that each seemed reasonable in isolation and a system that has silently accumulated the consequences of every one of them. This is the insight behind Mental Model 22. Controls drift over time because organizations are not static, and security controls are not self-maintaining. The question is not whether drift will occur. It will. The question is how quickly you will discover it, and whether you have built the mechanisms to find it before an attacker does. The foundation, understanding what drift actually is. To work with this principle fluently, you need a precise vocabulary. The terms here are not interchangeable, and confusing them will blur your diagnostic thinking. A security control is any measure, technical, administrative, or physical, that reduces risk by preventing, detecting, or responding to a threat. A firewall rule that blocks inbound connections on port 23 is a technical control. A policy requiring annual security training is an administrative control. A locked server room door is a physical control. Controls exist because someone, at some point, looked at a risk and decided to do something about it. A secure baseline is the defined, documented state that a system or environment should be in for those controls to be effective. The baseline is the ground truth. It says, this server should have these services disabled, these ports blocked, these files owned by this user with these permissions. The CIS benchmarks are one widely adopted standard for defining baselines. DISA SDIGs are another. Many organizations build custom baselines that combine elements of both with internal policy requirements. Controls drift is the divergence between what the baseline says the control should be and what the control actually is at any given moment. A firewall rule that was supposed to be set to deny is now set to allow. A service account that should have read-only permissions now has write access because someone elevated it temporarily during an incident and forgot to revert it. A configuration file that should be owned by root is now owned by a service account with world-writable permissions because a deployment script modified it. Each of these is a unit of drift. Accumulated, they constitute a degraded security posture. Configuration drift is one specific category of controls drift, and it is the most common and the most tractable to address with automation. Configuration drift refers specifically to deviations in system settings, file permissions, service states, and software versions from an established baseline. This is what tools like AWS Config, Azure Policy, and on-premises equivalents like Puppet or Chef are designed to detect and remediate. The harder and less frequently discussed category is what you might call governance drift. This is where the baseline itself becomes stale. The firewall rules document was accurate when it was written 3 years ago. Since then, 2 acquisitions happened, a cloud migration moved 80% of the infrastructure, and a new regulatory requirement changed the data handling rules. The controls have not changed. The environment has changed around them. And now the controls that were correctly specified for the old environment are incorrectly specified for the new one. Governance drift is not caught by a configuration scanner. It is caught by threat modeling, architecture review, and the habit of asking whether the controls that exist were designed for the world as it is or the world as it was. The governance side of this connects directly to what information security management means as a discipline. Governance provides the framework, policies, standards, procedures, against which the existence and effectiveness of controls is judged. When governance is weak, the baseline is weak, and drift becomes unmeasurable because there is nothing to measure against. A policy that says access to production systems must be controlled does not give you a baseline. A standard that says no user account shall have standing administrative access to production systems, and all privileged sessions must be brokered through the PAM solution and recorded gives you a baseline. You can measure against that. You can detect drift from it. This distinction matters enormously for how you talk about controls drift in any professional setting. The technical layer, configuration scanning, FIM, automated compliance checks, can only validate against a defined baseline. If the baseline is vague, the technical controls will tell you that everything is compliant while drift accumulates in the unspecified gaps. The structural tension, speed versus permanence. Every discussion of controls drift runs into the same structural tension. The conditions that make organizations effective at operating are the same conditions that generate drift. Organizations need to move fast. Engineers need to debug systems under pressure. Developers need to test integrations. Incident responders need to isolate affected segments immediately. All of these activities create exceptions to the baseline, and exceptions, by their nature, are departures from the controlled state. The problem is not that exceptions exist. Exceptions are sometimes necessary. The problem is that exceptions, once created, have a strong tendency toward permanence. The reason is structural. Creating an exception is easy and immediate. It requires one action, opening a firewall rule, elevating a permission, disabling a service, and it produces an immediate result. The engineer can continue their work. Removing an exception requires a second action that produces no immediate result. The system continues to function whether or not the exception is removed. There is no feedback loop. There is no alarm when the ticket is not created. There is no error message when the firewall rule stays open for a week after the debugging session ends. This asymmetry is fundamental. The creation of exceptions is reinforced by the organization's natural incentive to keep systems running. The removal of exceptions is reinforced by nothing except discipline and process. And discipline and process, under operational pressure, lose to the immediate need almost every time. The practical consequence is what you see in audit findings. 45 allow any firewall rules in an environment whose policy specifies strict least privilege network segmentation. Not because anyone decided to create 45 allow any rules. Because 45 separate debugging and troubleshooting sessions each created one rule and none of them were cleaned up. The accumulation is the disaster. Each individual decision was defensible. The aggregate result is indefensible. The resolution to this tension is not to eliminate exceptions. It is to time box them. An exception without an expiration date is a permanent change to the baseline under a different name. An exception with an expiration date, documented in a change management ticket, with a review requirement at the end of the window, is a controlled departure that the system is designed to reverse. Infrastructure as code makes this enforceable rather than aspirational. If the only way a firewall rule exists in production is by being declared in a Terraform configuration that is committed to a repository and reviewed before deployment, then an informal exception cannot survive a pipeline run. The infrastructure drifts back to its declared state automatically. Drift becomes self-correcting rather than self-accumulating. But infrastructure as code is not a universal solution. Legacy environments, operational technology systems, and on-premises infrastructure with complex interdependencies cannot always be fully code-managed. In those environments, the compensating discipline is continuous validation, not trusting that the control is still in its intended state, but regularly and automatically verifying that it is. The hardening baseline, what continuous validation is actually validating against. Before you can validate continuously, you need something to validate against. This means you need a hardening baseline, and you need to understand what a baseline is and is not. A hardening baseline is a documented specification of the secure state of a system. Its configuration, its permissions, its running services, its installed software, and the checksums of its critical files. It is derived from a combination of vendor security guidance, industry benchmarks like CIS, regulatory requirements like DISA SDIGs for government environments, and your own organizational risk decisions. The process of reaching a hardening baseline starts with a gap analysis. You take a fresh system or a representative sample of existing systems, and you run an assessment against your target benchmark. The assessment tells you, for each control point, whether the current state conforms to the standard. A server running a default Ubuntu installation might fail 40% of the CIS Level 2 benchmark checks. Those failures become your remediation backlog. You work through them, verifying that each remediation does not break the application that runs on the server, and progressively bring the system into a compliant state. What most organizations skip, and what creates enormous vulnerability, is the step of verifying that the baseline you established is actually correct. A baseline that disables a service that a critical application depends on is not a good baseline. It is an untested baseline. When someone discovers that the application fails without the service, they re-enable the service, often without updating the baseline. The baseline now describes a state the system has never been in and will never be in, and every subsequent drift assessment is measuring against fiction. This is why hardening must involve application teams, not just security teams. The security team can specify what the operating system configuration should look like. They cannot, without application knowledge, specify which of those settings are compatible with the applications that run on top of the operating system. The hardening baseline is a negotiation, not a dictate. The output is a documented state that is both secure and functional. That is the only baseline worth measuring against. The formal expression of a baseline in a compliance automation context uses the Security Content Automation Protocol, or SCAP. SCAP formatted content consists of oval definitions, which describe how to collect and interpret system state data, and XCCDF checklists, which describe the rules that the collected data must satisfy. When an automated scanner runs a CIS benchmark assessment, it is executing SCAP content. The advantage of this format is that it is machine-readable, versioned, and auditable. When you report to an external auditor that your servers are compliant with CIS Level 1, you can show them the exact SCAP content used, the exact results for each check, and the exact timestamp of the assessment. An external audit, however, is a point-in-time assessment. It validates the state of the environment on the day of the audit. The controls drift principle says that the state on the day of the audit is the worst possible proxy for the state of the environment on any other day. Audits verify the past. They do not secure the future. The assessment cadence that matters is not the annual external audit. It is the continuous automated scan that runs daily or hourly against every system in scope, comparing current state to baseline and alerting immediately on deviation. 4 tools and the drift they hunt. The tools that enforce continuous validation each address drift at a different layer. Understanding how they work, what they cost, and what they cannot see is the practitioner's way of knowing which combination to reach for. The first tool is Cloud Configuration Audit, the category exemplified by AWS Config and Azure Policy. These services continuously monitor the configuration of cloud resources, storage buckets, compute instances, network security groups, database settings against policy rules you define. When a developer creates an S3 bucket and forgets to enable server-side encryption, AWS Config detects the deviation within minutes and can trigger an alert, create a finding in your compliance dashboard, or invoke an auto-remediation Lambda function that enables encryption automatically. The cost of these services is low in dollar terms but moderate in operational terms. You must write and maintain the policy rules. You must tune them to avoid false positives when legitimate configurations match the pattern of a violation, and you must build the processes to triage and act on the findings they generate. What they cannot see is the application layer. They tell you that the S3 bucket has encryption enabled. They cannot tell you whether the application writing to that bucket is doing so in a way that is semantically correct, encrypting sensitive fields before writing them or failing to strip PII before archiving. The controls they validate are infrastructure level. The gaps they leave are application level. The second tool is File Integrity Monitoring, or FIM. FIM establishes cryptographic baselines, SHA-256 hashes, of critical system files and directories, and alerts when any monitored file changes. If an attacker gains access to a system and modifies a binary, replaces a configuration file, or installs a rootkit, FIM will generate an alert. On Linux systems, critical monitoring targets include the contents of etc., bin, /sbin, and /usr/bin, as well as specific application configuration directories. On Windows systems, the registry hives, System32, and application directories are the primary targets. The tool's value is precise. It tells you that something changed, what changed, when it changed, and if you are running an agent-based solution, which process made the change. The cost is the false positive management burden. Legitimate software updates, configuration management runs, and routine log rotation all touch monitored files. Tuning FIM to suppress the noise of legitimate changes without creating blind spots for malicious ones is an ongoing operational effort. What FIM cannot do is tell you whether a change is malicious. It tells you that a change occurred. The analyst must determine whether the change was authorized. This requires the change management process to be functioning correctly. If there is no ticket documenting an expected change, and a file changes, that is your signal. The third tool is Breach and Attack Simulation, or BAS. This category of tooling is qualitatively different from configuration scanners, where configuration scanning asks whether the controls are configured correctly. BAS asks whether they actually work. A BAS platform deploys agents that simulate attacker techniques, credential theft, lateral movement, data exfiltration, command and control beaconing, and measures whether your defensive controls detect, block, or are blind to each technique. When a BAS simulation successfully exfiltrates a test file to an external destination and no DLP alert fires, you know your DLP policy has a gap. When a simulated Mimikatz execution on an endpoint is not detected by your EDR, you know either that the EDR is misconfigured, the agent is not running, or the EDR signature database has not been updated. The value of BAS is that it validates the effect of the control, not just its configuration. The cost is significant. BAS platforms require careful scoping to avoid disrupting production systems, careful integration with your SIEM and EDR to avoid flooding your analysts with simulated alerts during validation runs, and significant expertise to interpret results and prioritize remediation. What BAS cannot do is be exhaustive. Attack simulation platforms are limited by the techniques in their library. Zero-day techniques, novel attack paths specific to your environment's unique topology, and logic-level attacks against business processes are outside the scope of automated simulation. The fourth tool is SIEM-based health monitoring, sometimes called meta-monitoring or alert health checks. The failure mode this addresses is subtle and serious. A log source goes silent, a firewall stops forwarding syslog, a Windows event forwarding subscription breaks, an EDR agent uninstalls during an OS upgrade, and nobody notices for days or weeks. During that window, the SIEM has no visibility into that source, meaning that any attack traversing it is invisible. The SIEM generates no alerts not because nothing happened, but because it received no data to analyze. Meta-monitoring addresses this by treating the presence of log data itself as a signal to monitor. If a firewall that normally sends 5,000 events per hour sends 0 events for 30 minutes, that is an alert. If an endpoint agent that checks in every 15 minutes has not checked in for 2 hours, that is an alert. The cost of meta-monitoring is the work of profiling normal log volumes for every source. A source that legitimately has low traffic at certain times should not generate alerts during those times, and the ongoing tuning as sources are added, removed, or change their behavior. What meta-monitoring cannot see is adversarial manipulation of log streams. A sophisticated attacker with access to the log forwarding infrastructure can suppress their own activity from the SIEM while leaving other events flowing normally. This is why log immutability, sending logs to a write-only, append-only destination that the logging systems themselves cannot modify, is a control that belongs alongside meta-monitoring, not as a replacement for it. Implementation, building the continuous validation engine. Let us take the conceptual framework into operational reality. 2 implementation scenarios capture the challenge at different levels. The first is implementing a configuration compliance scan against CIS benchmarks for a mixed Windows and Linux environment. You are starting from a state where no formal baseline exists. The first step is benchmark selection and scoping. You choose CIS benchmark level 1 for Windows Server 2019 and CIS benchmark level 1 for Ubuntu 22.0 for LTS. Level 1 is appropriate for most production environments because it applies settings that have been validated against typical operational requirements. Level 2 is for environments with higher risk tolerance for operational friction. Some of its recommendations will break applications that depend on specific default behaviors. You download the benchmark definitions and import them into your vulnerability scanner or compliance scanning tool. Before you run a scan against production systems, you run it against a single representative test system for each OS type. The output, a list of passing and failing controls, typically hundreds of line items, is your gap analysis. You then work through the failures in 2 passes. The first pass is to identify controls that are clearly applicable and remediable without application consultation. These are controls like disabling Telnet, setting the maximum password age, enabling the Windows firewall. You remediate these and rescan to verify. The second pass is to identify controls whose remediation requires application team input. Controls around service states, file permissions on application directories, network binding configurations. You schedule working sessions with each application team to review these controls and determine whether remediation is safe. Once you have a validated baseline for each OS type, you build it into your configuration management system, a Puppet manifest, an Ansible playbook, or a cloud-native equivalent. The baseline is now expressed as code. A daily automated scan runs the assessment against every server in scope. Deviations are logged and ticketed automatically. A compliance dashboard shows the percentage of systems passing each control, trended over time. When a new server is provisioned, it is automatically assessed at provisioning time, and its provisioning fails if it does not meet the baseline. The baseline is enforced at birth, not discovered after the fact. The second scenario is implementing file integrity monitoring on a sensitive directory containing application configuration files. This is a more surgical implementation. You identify the directories that contain configuration files whose modification could compromise the application's security posture. Typically the directory containing the application's main configuration, its credential files, and any scripts run by the application at startup. You establish the baseline hash for every file in these directories using your FIM tool. Tripwire, OSSEC, WASA, or OSQuery are common choices. You configure the tool to alert when any file in the monitored set changes. The first 2 weeks of operation are the tuning period. You will discover legitimate changes. The application reads a configuration value, writes a session cache, logs a startup timestamp that are touching monitored files. You adjust the monitoring scope to exclude dynamic files from the monitored set. You also discover that your deployment pipeline modifies configuration files as part of every deployment, which will generate alerts on every release. You address this by integrating FIM suppression with your change management process. When a deployment is approved, an automated step creates a temporary suppression window in the FIM tool for the affected directories, and then closes it after the deployment completes. Any file change outside an approved suppression window is a genuine alert. The thing that makes this implementation succeed or fail is what happens after an alert fires. FIM is not a detection system that produces a verdict. It is a sensor that produces a signal. If the signal is not responded to within a defined time window, if the analyst queue is too long, if the alert is too low a priority, if there is no runbook for what to do when a configuration file changes unexpectedly, then the FIM is operational theater. It is generating data that proves nothing was done with it. The implementation of the detection control is only as valuable as the response capability paired with it. When validation fails, 3 diagnostic narratives. The troubleshooting scenarios for controls drift are some of the most instructive in security operations, because they reveal the gap between the map and the territory, between what your monitoring tells you the state of the environment is and what the environment's state actually is. The first scenario involves patch compliance that looks perfect until a penetration test proves otherwise. The metrics dashboard shows 98% of servers patched against the target vulnerability. A scheduled penetration test runs 2 weeks later and successfully exploits the vulnerability on 12 servers. The question is how 12 servers can be both patched and exploitable. The diagnostic process starts by pulling the agent-side evidence. Your patch management tool reports patch status based on data collected by an agent running on each server. For each of the 12 affected servers, you query the agent directly. What does the agent report as the status of this specific patch? If the agent reports installed, you have a data quality problem. The agent's data does not reflect reality. This happens when an agent fails silently after reporting a patch as installed, but before the actual installation completes. or when the agent's reporting database has been corrupted. The fix involves verifying the patch state directly on the server using a credentialed vulnerability scanner, Nessus or Qualys, rather than relying solely on agent telemetry. If the agent report's not installed on some of the 12 servers, you have a coverage gap. The agent is correctly reporting an unpatched state, but the dashboard aggregation is incorrect. This happens when the coverage percentage is calculated based on managed assets only, and the 12 servers were not registered in the asset management system at the time of the calculation. Unmanaged assets look like compliant assets in a denominator-based metric because they are not counted. The fix is to cross-reference your patch management asset list against your network discovery data. Every IP that responds on your network should appear in your asset list. The ones that do not are your blind spot. This scenario is a perfect illustration of why the metrics you choose determine what you can and cannot see. A patch compliance percentage that uses managed assets as the denominator will always look better than the actual state of the environment. If you want a metric that reflects reality, you need a metric that uses the discovered network population as the denominator, which requires accurate asset discovery, which requires continuous network scanning, which is a control in itself. The second scenario involves a legacy application with compensating controls that has drifted into an exposed state. The application cannot be patched, the vendor no longer provides updates, and the business depends on it for a critical function. Compensating controls were applied 18 months ago. A WAF rule blocking known exploitation patterns, a network ACL restricting access to the application to a specific management VLAN, and a dedicated IDS signature tuned to detect exploitation attempts. An audit 6 months ago found everything in order. A new audit finds that the ACL restricting VLAN access has a rule that allows traffic from the production VLAN, as well as the management VLAN, making the application accessible to a significantly larger population of internal hosts. The diagnostic question is when this happened and how it was introduced. You pull the change management records for the ACL on the controlling switch. There is no change management record for the offending rule. You pull the switch configuration backup history, if you have one, and compare the current configuration to the configuration from the previous audit. The rule appears sometime between the audit date and 6 weeks ago in a window of 9 months. You query the network device log archive for changes to the ACL. If the switch was not logging configuration changes to your SIEM, this is where the investigation stalls. If it was, you find a change committed by a service account, a deployment automation account, that was deploying a new application to the production VLAN and modified the ACL to allow connectivity for the new application's required ports, inadvertently broadening access to the adjacent legacy application service. The fix has 2 layers. The immediate fix is to remove the offending rule and restore the intended ACL state. The structural fix is to ensure that ACL changes are never made by automation accounts without explicit approval. Automation should apply declared state from a configuration repository, not make ad hoc changes, and that every ACL change triggers a compliance check that compares the new state to the documented baseline for that device. The third scenario is the one that tests organizational maturity most directly. A SIEM migration is completed. The security team reports successful migration. Within 2 weeks, the detection engineering team notices that a specific correlation rule, one that detects lateral movement via RDP, has generated 0 alerts since the migration, despite the environment having significant internal RDP activity. The investigation follows a structured path. First, you verify that the log source is actually delivering data. You query the SIEM for Windows Security Event 4624, successful logon, from any source. If these events appear, the log source is functional. Second, you verify that the correlation rule is enabled and not paused. In some SIEM migrations, rules are imported in a disabled state to prevent alert storms during tuning. Third, you verify that the field names used in the rule logic match the field names in the new SIEM schema. This is the most common failure mode in SIEM migrations. The old SIEM might have called the logon type field logon type. The new SIEM might call it winlog, event data, logon type. A rule written for the old schema and imported unchanged into the new SIEM queries a field that does not exist in the normalized event, finds no matching events, and silently produces no alerts. The rule is active. The data is present. The rule and the data speak different schemas, and the SIEM does not raise an error because a query that returns 0 results is not the same as a query that produces an error. The resolution requires auditing every rule in the SIEM against the new schema and verifying that each field reference resolves correctly. For a large rule set, this is done programmatically. You extract all field names from all rules and cross-reference against the schema documentation for the new platform. The broader lesson is that detection rules are controls, and they drift. They drift when the log schema changes, when the data source changes, when the environment changes in a way that makes the detection logic no longer match the behavior it was designed to catch. Detection health monitoring, the practice of generating synthetic test events that should trigger each rule and verifying that alerts are produced, is the specific form of continuous validation that applies to the detection layer. The role lens, 3 seats at the same problem. The experience of controls drift looks different depending on the role you occupy. The same underlying problem manifests in ways that require different tools, different time horizons, and different success criteria. The compliance and audit professional encounters controls drift as the gap between what the policy says and what the evidence shows. When a compliance officer runs a quarterly access review and discovers that 18 former employees still have active accounts in the directory, the policy says accounts are disabled within 24 hours of termination. The drift is the 18 accounts. Each one represents a control that was supposed to fire, the joiner-mover-lever process that triggers account deactivation, and did not. The audit finding is straightforward. But the compliance professional's job does not end with noting the finding. It extends to root cause. Was the HRTYT notification process broken? Was the automation that processes termination events misconfigured? Was it a subset of employees, perhaps contractors, who were not in the scope of the automated process? Each root cause implies a different fix, and the fix is not just remediating the 18 accounts. It is implementing continuous validation so that the next monthly account review is not needed. Because the automation catches and corrects the drift within hours of the termination event, not months. The detection engineer encounters controls drift as the progressive degradation of alert effectiveness. A detection rule that was high fidelity 18 months ago starts producing either false positives or false negatives as the environment changes. A rule designed to detect base 64 encoded commands in PowerShell activity starts generating 100 times more alerts after a new software deployment tool uses base 64 encoded commands as its standard operational method. The rule is technically correct. The environment has changed around it. From the detection engineer's seat, this requires distinguishing between 3 possibilities: a genuine attack spike, a change in benign application behavior that matches the detection pattern, or a bug in the rule logic. The methodology for making this distinction involves pulling a sample of the new alerts and analyzing whether they share a common source, a common process, or a common timing pattern. A genuine attack spike tends to be distributed across many sources with irregular timing. A benign application change tends to produce alerts concentrated on specific hosts or user accounts associated with the new application, at regular intervals that match the application's operational pattern. A bug in the rule logic tends to produce alerts that, on inspection, do not actually match the behavior the rule was designed to detect. The regex is overbroad, the threshold was set incorrectly, or a field is being evaluated with a logic error. The security automation engineer encounters controls drift as the problem of scale. When you are responsible for validating that controls are functioning across hundreds or thousands of systems, manual verification is not a viable approach. The automation engineer's contribution is building the infrastructure that makes continuous validation possible. The scheduled pipeline that pulls configuration state from every system, compares it to the declared baseline, and produces a drift report. The hardest part of this work is not the technical implementation. The hardest part is handling the edge cases, systems that cannot be reached by the automation agent because they are in a network segment with different routing rules, systems whose configuration baseline is legitimately different from the standard baseline because of a documented exception, systems whose configuration is managed by a separate team and should not be reported as non-compliant by your tool. Building automation that is accurate, that correctly identifies genuine drift and correctly suppresses known exceptions, is the operational discipline that separates useful compliance automation from noisy dashboards that people learn to ignore. Case scenario: the 2-year accumulation. You are a security architect at a mid-sized SaaS company. The company has a documented security baseline, a gold image, for all web-facing servers. The gold image specifies a hardened Linux OS, a minimal set of open ports, strict file permissions, and a WAF configuration that blocks the OWASP top 10. When servers are provisioned, they are built from this image, and the compliance team signs off that the baseline is met. The constraint is the engineering culture. The company moves fast. The engineering teams have broad access to production infrastructure. The change management process requires a ticket for planned changes, but the engineering culture treats emergency debugging as exempt from the process. The implicit rule is that you fix the problem first and document afterward. Documentation afterward in practice means documentation if you remember to do it. 2 years pass. A new CISO joins and commissions a security posture assessment. The assessment team runs automated configuration scans against a representative sample of production web servers. The results are alarming. 45 firewall rules exist with allow any source conditions, meaning they permit traffic from any IP to reach the specified service. None of these rules appear in the infrastructure as code repository. The file integrity monitoring system, which was deployed 18 months ago, has not generated a single alert in 6 months because its agent was silently failing on the new kernel version deployed in the last OS upgrade, and nobody noticed because meta-monitoring was not configured for FIM agent health. 3 servers are running a version of the web server software that is 2 minor versions behind the current release, which contains a patch for a known XSS vulnerability. The WAF is in detection-only mode on one of the 5 load-balanced server nodes, meaning attacks on sessions that route to that node bypass active blocking. The detection-only mode was enabled during a debugging session 11 months ago and never reverted. The posture assessment presents these findings to the CISO and the CTO. The business decision is to fix the immediate issues and build a continuous validation capability that prevents this class of finding from accumulating again. The trade-off that must be made explicit is between the speed of the engineering culture and the rigor of continuous compliance. The immediate remediation follows a specific order. First, the WAF mode issue, because it represents an active security gap on production traffic. You revert the detection-only configuration to blocking mode and verify that no traffic was being blocked that should not be. Second, The 45 allow any firewall rules. You cannot simply delete all 45. Some of them may be supporting legitimate traffic that is not documented anywhere. You pull network flow logs for each rule and identify which rules have had traffic traversing them in the last 30 days. Rules with no traffic in 30 days are deleted with minimal risk. Rules with traffic require investigation. You identify the destination services, the source IP ranges actually appearing in the flows, and whether a more specific rule can replace the allow any. This process takes 2 weeks. You end with 22 rules removed outright, 18 replaced with specific rules, and 5 that require application team consultation to understand before modification. Those 5 go into a risk register as known exceptions under active investigation. Third, the FIM agent failures are remediated by updating the agent to the version compatible with the current kernel, and meta-monitoring is configured to alert if any FIM agent has not checked in within 4 hours. Fourth, the web server versions are patched through the standard change management process. The structural change is the more important work. You work with the engineering team to establish infrastructure as code as the authoritative source of truth for all firewall rules. Any rule that does not appear in the Terraform repository is by definition unauthorized. A CI/CD pipeline step runs before every deployment. It compares the declared state in the repository against the actual state on the infrastructure, and fails the deployment if there are undeclared rules. An automated job runs nightly to detect rules that exist in production, but not in the repository, even outside deployment cycles, and creates a JIRA ticket for each finding with a 7-day resolution deadline. The exception process is redesigned. Engineers who need a temporary firewall rule for debugging must create a ticket that specifies the rule, the reason, and a maximum duration of 48 hours. The automation that enforces the rule also enforces its expiration. After 48 hours, the rule is removed automatically. The engineer receives a notification 1 hour before expiration so they can extend if the debugging is still in progress, but extension requires a new ticket with a manager approval. The friction is intentional. It is not enough friction to block legitimate debugging. It is enough friction to make the alternative, completing the debugging task and closing the exception, the path of least resistance. The 30-day audit-only period for the auto remediation script is the critical safety mechanism. The script runs for 30 days, identifying every rule it would remove if it were in active mode, and sending the removal candidates to a distribution list that includes the engineering leads. During this period, 5 rules that would have been incorrectly deleted are identified and added to the legitimate exceptions list with documentation. After 30 days, the script moves to active mode with high confidence that its removal logic is correct for the current environment. The outcome, 9 months later, is that the quarterly configuration scan shows 97% compliance with the baseline across all production servers. The 3% of deviations are legitimate documented exceptions, each with a ticket and an owner. The number of open firewall rules in production matches the number of firewall rules in the Terraform repository within a margin of 0. The CISO can present this posture to the board with evidence, not assertions, but time-stamped scan results, not a point-in-time audit, but a trending compliance rate that has moved from a catastrophic baseline to a maintained steady state. The trade-off that was made is documented. The engineering team accepted that infrastructure changes require code review and approval. In exchange, they received a clear, fast path for emergency exceptions with a time limit. The security team accepted that the auto-remediation script will never be perfect and that there will be edge cases requiring manual intervention. In exchange, They received a continuous validation capability that makes multi-year drift accumulation structurally impossible. Neither side got everything they wanted. Both sides got a system they can operate in. Closing, the practice of distrust. What controls drift teaches you, ultimately, is a particular kind of professional distrust. Not suspicion of people, though that has its place, but a systematic distrust of the assumption that things which were once put right will stay right on their own. Security professionals who have internalized this principle think differently about their environment. When a colleague says that firewall was configured correctly last year, their instinct is not to accept this as current fact. It is to ask, how do we know it is correct today? When a report shows 99% patch compliance, their instinct is not to feel satisfied. It is to ask, what is in the 1%, and how do we know that the 99% was verified correctly and not just reported by agents whose data we have not independently validated? This is not paranoia. It is a calibrated response to the nature of complex systems under operational pressure. Things change. People make well-intentioned decisions that have unintended consequences. Automation that worked yesterday fails silently today. The environment that your controls were designed for continues to evolve while the controls themselves remain static. The practice of validating continuously is the practice of maintaining a current and accurate model of your own security posture, rather than a historical one. And the reason this matters is not abstract. The attacker who is looking at your environment right now is not working from the model you had 2 years ago. They are working from the model as it exists today, including every exception that was never cleaned up, every agent that went silent, every rule that drifted from its intended configuration in the 9 months since the last audit. Your job is to see your environment as clearly as they do, not once a year, not once a quarter, continuously. That is the discipline, that is the control. End of session mental model. Controls drift over time, validate continuously.